This video here will talk you through the notes for geometry of simultaneous linear equations with two variables, so that's 2f. Now you'll recall from all the way back in probably year 9 that when you solve a system of linear equations with two unknowns, there's three potential things that can happen. The first is we get a unique solution. So here's our unique solution here. And to get a unique solution, there's only one thing that needs to happen, and that is that the gradients can't be the same. The minute the gradients are not the same, that means that you are going to get a unique solution. And the y-intercept can be the same or it can be different. It doesn't really matter whether they've got the same y-intercept. Here they don't, okay, or they do have the same y-intercept. So we're not too worried about the y-intercept, but we are worried about the gradients, and we want them to be different for outcome 1. Now outcome 2 is there's infinitely many solutions, and that's when you have the same gradient, same y-intercept. The final situation is outcome 3, there's no solution, same gradient and different y-intercepts, so the lines run parallel to each other. Okay, so let's try that out. So consider the simultaneous linear equations that, and we want to find the values of m and k such that the system of equations has no solution. So no solution means m1 equals m2, it'll have the same gradients, and c1 can't be the same as c2. Alright, so what we want them to do is it's lines that run parallel to each other. So once we have written this down, what we're going to do is get both of these equations into y equals mx plus c form. So our first one is going to be y equals, subtract that thing from both sides, negative m c m take 2x plus 2. Right, this one here is going to be 2y equals negative mx plus k, y equals negative mx on 2 plus k on 2. Alright, so now we're going to grab the gradients and equate them. So this gradient here is negative m take 2, and we're going to equate that with this one here, which is negative m on 2. So let's multiply by 2 and dump the negative at the same time. So we've got 2 m take 2 equals m, 2m take away 4 equals m equals 4. Right, so what this is saying is there's going to be no solution when m equals 4, and let's just check out the y-intercepts. So we're going to say that c1 can't equal c2, so we've got 2 can't be the same as k on 2, which is this one here. K can't equal 4. So what this is basically saying is for this system of equations, if m is equal to 4 and k is not equal to 4, we're going to get no solution. So let's just see what that might look like. And I'll just draw both of these graphs in GeoGebra. Okay, so the first one is m take 2 x plus y equals 2, and the second one is mx plus 2y equals k. That's not going to work the way I want. I need to multiply between them. Alright, so now I'm going to set both of them to, or I'm going to set m to 4. And we can see here that when m is equal to 4, oh come on, yep, okay, there we go, that the lines are parallel, i.e. there's no solution. But it also said that k can't be equal to 4, and I wonder why not. Because of course, they become the same function when k is equal to 4. Okay, so that's not no solution, in fact that's gone to infinitely many solutions. So that's basically what we're doing, is we're working out the values of these parameters here, m and k, such that it meets this condition. So the other condition is going to be infinitely many solutions, and infinitely many solutions is this case here. m1 is the same as m2, and c1 is the same as c2. And we've already got that, okay, because we know that m1 is, or m is equal to 4, This one here, instead of k not equal to 4, it's going to be k equals 4. Okay, and the final one is a unique solution. And a unique solution can be found by having different gradients. And C1 and C2, well, we're not really worried about the y-intercept. So this one here is going to be m can't equal 4. And what can k be? Well, k can be any real number. Okay, so give it any real number and you'll still get a unique solution. The only condition we're worried about is what m is. So to do that on Mathematica, it's a fairly feisty looking function there, but this will allow you to visualize this. So you can see why I did it on GeoGebra just for the moment. But once you get that copied into your notebooks for Mathematica, it'll be fairly easy to slam out any problem like this. Alright, so this was on the 06 VCAR Methods Exam 2, and hardly anyone got it. So roughly 1 in 3 students was getting this correct. So we have no solution for these. So the minute you see this question comes up all the time, by the way. You're going to say M1 equals M2, and no solution means that the C1 can't be the same as C2. Okay, so we're going to get parallel lines. So again, it's the same process for this problem. So we're going to go negative M take 2x, what is it, plus 6, y equals negative, oh my god, I keep going to write a plus. Alright, the other one was y equals, and I'm going to put negative 2x over m take 3 plus m take 1 over m take 3. Okay, so ready to pair the gradients. So we've got negative now, because this is exam 2, you could just write this out and run that through a solve in Mathematica. Now don't forget, the syntax requires you to put the double equal sign and the comma m, and that'll get it for you. But it might be even quicker just to run the numbers. Okay, so let's just see what happens here. So I'm going to cross multiply here and divide through by negative 1 straight away. So I'm going to get m take 2, m take 3 equals 6. Alright, then let's expand that. M squared, take 2m, take 5m, plus 6 equals 6. Subtract 6 from both sides. M squared, take away 5m equals 0. Factorize that thing. M take 5 equals 0. M equals 0. M equals 5. Alright, so now that we've found this scenario, so it's suggesting that it has no solution for m equals 0 and m equals 5. But what about the y-intercepts? So what we need to do is pair off the y-intercepts and just see what happens here. So m take 1 over m take 3 can't be the same as 6 on 3, which is 2. M take 1 not equal to 2 m take 3, 2m take 6, m take 1, what is it, m not equal to, m5 not equal to 5. So this one here suggests that m can't be equal to 5. And so what that does, that means that although you found that there's these two scenarios here to produce the same gradient, this says, oh, but if you want this exact condition, which is no solutions, m can't be 5. So what that does is that actually voids that solution, meaning that E is our answer. Alright, So something a little bit unique to the Cambridge textbook is this idea of using parameters to describe infinitely many solutions. So haven't seen it on too many exams, but it's a good skill to know. So explain why the lines that one and that one have infinitely many solutions in terms of gradient and y-intercept. Well, they're the same function, because if I times that by 2, and that by 2, basically I'm going to produce this. So what we're going to do is, in terms of gradient and y-intercept, we'll just go 3y equals negative 4x plus 12, y equals negative 4x on 3 plus 4. This one here, 6y equals negative 8x plus 24, y equals negative 8x on 6 plus 4, which is negative 4x on 3 plus 4. So notice that those are the same and those are the same. So m1 is the same as m2, negative 4 on 3 is the same as negative 4 on 3, and c1 is the same as c2, 4 is the same as 4. So therefore they are the same function, or infinitely many solutions. So 5 possible solutions to this. Well, remember there's infinitely many, so we can get 5 solutions by simply jamming in a value for x and solving for y. So let's do it. When x is equal to 0, that cancels out, giving us 3y equals 12, y equals 4. We could do 1, which is 4, 8, 8 on 3. We could do 2, which is 8, 4, 4 on 3, ... So I'm not going to do 5 possible solutions because I just keep going. Now what about if you had to list all of the possible solutions? Where's my mouse gone? So that's more difficult, and well, it's difficult because there's infinitely many solutions. So what we do here is we describe all the possible solutions by using a parameter, and this Cambridge textbook uses lambda as the parameter. I don't know why, but they do. So what we're going to do is we're going to say x is equal to lambda, where lambda is an element of all real numbers. Now that we've done that, let's pop it in. So we've got 4 lambda plus 3y equals 12, and we're going to get y. So 3y equals 12, take away 4 lambda, y equals 3 goes into 12, 4 times, take away 4 lambda on 3. So there is our y value, and there is our x value. So x is lambda, and y is 4, take away 4 lambda on 3. And so basically the solutions are saying if you want to get an ordered pair on the for these lines here, then these are going to be the coordinates, i.e. choose a value for lambda, 2, 3, anything from the real number system, jam it into this, and that's going to be a possible solution. Now Mathematica produces some interesting output for these ones here. So you can see here I've run a solve for the 2 equations, and Mathematica has given me this as a solution. Y is equal to 4 take away 4x on 3. And so they don't use lambda, they just use or give the y solution in terms of x. So when you see this happen, when you expect 2 solutions to be produced as the result of solving simultaneous equations, and you only get this one here, you got to know that there's infinitely many solutions. So you interpret the y solution as 4 take away 4 and whatever your parameter is. We'll use lambda just to be consistent, and the x is lambda. So that's how to interpret that. So find the solutions if there are any for these equations here. Well, there is lots. In fact, it's the same function. 2x 2y equals 12 is the same as that. So because there's going to be infinitely many solutions, let's go x is equal to lambda, where lambda is an element of all reals. Now let's pop it into, well, you can pop it into either, but we'll throw it into this one here. Lambda plus y equals 6, y equals 6 take away lambda. And there's our y solution. So we've got our x there and our y solution there. So we can write it up as an ordered pair, you don't have to. But that's how I produce all of the solutions. Okay, so all of the ordered pairs are this, where if you choose lambda equal 1, then this will be 6 take away lambda, which is 5. And that is one possible solution of infinitely many. The work today, knock over 2f and complete the simultaneous equations worksheet.